function between representations, which our books refer to as a morphism. You could also call it a homomorphism. So if I have two representations of the same group G, a morphism is a linear map T from V to W between the two spaces such that psi sub G following T equals phi G preceding T. And this is for all elements of the group. By the way, another name for this is intertwining operator. You'll see that sometimes. So we'll think of this as the right kind of function relating to the two representations. Just like for groups, the right kind of function is a homomorphism. Let's notice if T is an isomorphism of vector spaces, then you have a T inverse, which goes in the other direction. And the condition can be rewritten as psi sub G equals T phi G phi T inverse. In other words, that's the same notion as an equivalence. But if T is not an isomorphism of vector spaces, this doesn't make sense. And this is the right way to write the identity. So here's some notation. If I have vector spaces, I'll write HOM VW for the space of all linear maps from V to W. Let's notice that this is also a vector space, because I can add maps, linear maps, and get a new linear map, or multiply them by scalars. Well, if I have two representations, which maybe live in two vector spaces V and W, then I'll write HOM sub G phi psi for the set of linear maps which are morphisms, such that psi gt equals T phi G for all elements of the group. So that's the set of morphisms of representations from phi to psi. This is a vector subspace of the set of all linear maps. In other words, if T1 and T2 are morphisms of representations, then so is C1 T1 plus C2 T2, where C1 and C2 are scalars. That's something that's just very easy to check. Just verify the condition for a morphism. Let me record the following fact, which is going to be very important for us. If T from V to W is a morphism of representations from phi to psi, so this means that phi is a representation in V, psi is a representation in W, then the subspaces, well, I can take the kernel of the linear map, that's a subspace of V, and I can take the image of T, that's a subspace of W. Those are invariant subspaces. This is very easy to check just from the definitions. Let's do the kernel. If I have a vector in the kernel of T and I have an element of the group G, then if I form phi G of V and then apply T, well, because T is a morphism, this is the same as psi G of T of V, but V is in the kernel, so that's 0. And then that's 0. So phi G carries that subspace, the kernel, into the kernel. Oh, and this also applies, by the same argument, to phi sub g inverse. So that means I can replace this subset relation with equality. The proof that TV is a subspace is very similar to that. We've seen that kind of argument before, really.